Hi everyone, my name is Xu Shi. I'm going to continue the discussion of large multimodal models, and I'm going to introduce four more models in the LMM family. So the first model we are going to look at is another family member in Poly family, which is Poly 3. So the motivation of Poly 3 is quite straightforward. It focuses on a smaller scale model as mentioned in Poly, scaling of vision language models to tens and even hundreds of billions of parameters has shown ever-increasing performance, like we discussed Flamingo with 80 billion, and the Poly, which focus on scaling up the language part of the LMM. But Poly 3 point out that models at a smaller scale remain critical, so it presents Poly 3 with only 5 billion parameters. And there are three components in Poly 3 that help it to achieve a still competitive performance. The first is a contrastive pre-training of image encoder on web-scale image text data, and an improved dataset mixture inherited from Poly, and also it will train the Poly 3 at higher resolutions. And there are two dominant ways to pre-train image encoders, and the author of this paper actually focused on compare these two dominant ways using the Poly framework, which are classification, pre-training using large weakly labeled datasets, and contrastive pre-training on web-scale noisy data. So let's first look at the contrastive pre-trained seq lib. So we should first recap the standard softmax loss for language image pre-training. The objective of this language image pre-training is usually given a mini batch B equals I1, T1, I2, T2, etc. of image text pairs. The learning objective encourages embeddings of matching pairs to align with each other while pushing embeddings of unmatched pairs apart. And looking into the loss function, we should notice that it actually consists of two terms. One is from image to text softmax, and another is from text to image softmax. And notice that because of the asymmetry of the denominator, we usually need to compute the normalization term twice, which is really computationally inefficient. And this kind of loss function is commonly used in model like CLIP, which require a global view of the pairwise similarities for normalization, batch-level softmax-based contrastive loss, and apply twice to normalize the pairwise similarity scores across all pairs of data. Okay, so after recapping the standard softmax logs, we look into what is seq-lib. So seq-lib is actually a paper that proposed the sigmoid-based loss, which different from the softmax, it actually process every image text pair independently. So looking to the formulation, it is way more simple than the previous one. We only introduce an additional label for a given image and text pair, which is stat ij, and it will turn this learning problem into the standard binary classification on the dataset of all pair combinations. So whenever there is a matching pair, there is a positive labels related, and if there is an unmatched pair, the negative label is signed. So this is actually better for a multi-label classification problem, as there is no need to compute global normalization factors, which is the denominator we mentioned in the previous formulation. After looking to the cyclic, let's look at the UL2 framework, which is unifying language learning paradigms. So the existing pre-trained models are generally geared toward a particular class of problems. And that is the motivation of this paper, which asks why should the choice of the pre-trained LM depend on the downstream task? So in order to understand this problem, let's recap what is the current pre-training objectives we have for large language models. So usually there are three, which is causal LM, which use all previous time steps as inputs to the model to predict the next token, which is target. And there is also prefix LM, which use past tokens as inputs, quite similar as causal LM. The only difference is like they consume the inputs bidirectionally. And the other one is a span corruption, which is a little different. It leverages all uncorrupted tokens from the past and futures as inputs for predicting the corrupted span targets. And we can notice that for each of these pre-training objectives, can always reduce one pre-training objective to another. So for example, in the span corruption objective, when the corrupted, which is target, is equal to the entire sequence, the problem will become an LM problem. So after noticing that common between each of the pre-training projective, the author actually proposed span corrupt, which is function used to generate inputs and targets of the denoising tasks. And there are a parameterization of this function, which has introduced three parameters: mu, that is the mean span length, the R is the corruption rate, and N is the number of corrupted tokens or spans. It can be a function of input length L and the span length mu. So given an input text, this function will introduce corruptions to the span of lengths that are drawn from the normal or uniform distribution with mean of mu. So for example, to express the prefix LM objective, we can set mu equals L minus P, where P is the length of the prefix, and R, which is corruption rate, is equal to 1.0 minus P over L, with N equals 1, which means there's only one corrupted spans. And after corruption, the input text is fed to the denoising task, and the corrupted spans are used as targets to be recovered. So after learning the span corrupt function, based on the fact that a strong universal model has to be exposed to solving diverse set of problems during pre-training, given that pre-training is done using self-supervision, authors argued that such diversity should be injected to the objective of the model. Otherwise, the model might suffer from lack of center ability. And motivated by this, they propose, as well as that current class of objective functions, the author defines three main paradigms that are used during pre-training, which is R denoiser, S denoiser, and X denoiser. So we can look into each of this paradigm. We can notice a different pattern of corruption. So for R denoising, it more focus on mimicking the objective of span corruption, and spans are short and potentially only useful to acquire knowledge instead of learning generate fluent tasks, whereas the S denoising is way more like a prefix LM objective. So the context, which is prefix, will retain a bidirectional receptive field. And finally, the X denoiser, which target to recover a large part of the input given a small part of it, is actually an interpolation between a regular span corruption and the language model, like objectives. And besides of that, The author also introduced the notion of paradigm shifting while mode switching. So during pre-training, we'll fed the model with extra parent token, which is RSX. So that will help the model switch skills between different tasks and operate on the mode that is more suitable for a given task. So after learning the main components of Poly 3, let's look into the stages of training. So Poly 3 actually have several different stages. So for the first stage, it will do a unimodal training where each of the components is trained separately. So the image encoder is pre-trained contrastively on an image text files from the web, following the cyclic training protocol. And the text encoder decoder, which is 3 billion language model, is trained following the mixture of denoisers. And the second stage is the multimodal training, where we will frozen the contrastive vision encoder and only train on a multimodal task and data mixture, which is retained from Poly by keeping the encoder frozen at the resolution 224. And after that, there is a resolution increase, which will fine-tune the whole model. So at this moment, both the contrastive visual encoder and the language model is unfrozen, and they are trained to either 812 or 1064 resolution. So looking at the experiments conducted in this paper, so one important experiment being conducted is the comparison between a classification-based language vision encoder and the contrastive-based vision encoder. So we can notice that one pre-trained for the classification on the GFT dataset, and the other is actually contrastive pre-trained on the WebLead dataset using the cyclic protocol. And from the following table, we can notice that actually cyclic models excelled in tasks like captioning and more complex tasks like a text VQA here or RefCoco. So the harder the problem is, the more benefits the cyclic models can provide. And there are other experiments being conducted. For example, it will fine-tune and evaluate on the video captioning and video QA, and notice that Poly 3 is not being pre-trained with any video data. So this actually highlights the benefits of adopting a contrastive VITs. And during this experiments, what they did is they concatenate the vision tokens for each frame for at most 16 frames with a fixed temporal stride. So this is all about Poly 3. Okay, so let's go to the second model we are going to talking about, which is EMO 2, which is a generative multimodal models. And it points out that the GMM is actually an in-context learner. So let's first quickly catch up or recap what is in-context learning. So in-context learning is actually refers to the ability to solve a multimodal task in context with only a few demonstrations or simple instructions. So we can look into the example here, and we can look at the bottom one here. So the model is actually given 3 examples. A prompt, like the subject A with a city in the background, and the image. So this is as example 1, example 2, example 3, and it given a prompt to the model, which is the subject A wearing a rainbow hat, and the model is expected to generate an image following the previous examples, and this is what EMO 2 is able to generate it. So the motivation of EMO 2 is actually it Notice that multimodal tasks usually encompass anything involving understanding and generation in single or multiple modalities, and the previous multimodal systems are largely rely on designing task-specific architecture and collecting a sizable supervised training set. But we notice that humans can solve a new task in context, which means with only a few demonstrations or simple instructions. That is why this paper is actually demonstrate that a scaled-up multimodal generative pre-trained model, which is around 37 billion parameters, can harness a similar in-context learning abilities. So let's first look at the architecture of EMO2, and in order to understand what is the architecture of EMO2, we better first understand a previous version of EMO2, which is EMO, because like EMO2 is heavily built upon EMO. So in EMO's model architecture, there's actually 4 components. There's a visual encoder, there's a causal transformer, there's a multimodal modeling component, which is LLM, and there's a visual encoder. So we can see first the image will be encoded into a dense visual features, and then transform the encodings into a fixed number of n visual causal embeddings, right? These causal transformers, and these visual embeddings combined with the text tokens are fed into the multimodal modeling with LLM to form a multimodal sequence using and then perform a unified autoregressive modeling. And in the inference, there is a fine-tuned visual encoder, a decoder being used to decode these visual embeddings into a realistic image. That is why EMO2 is able to generate image. And we should notice that the goal of this causal transformer is to better capture the characteristics of images and achieve a unified modeling of different modalities. And all this causal transformer doing is just transform these embeddings generated by encoder into a fixed number of n visual causal embeddings. And besides of this causal transformer, what else we should actually pay attention to is this decoder, which is initialized by stable diffusion. And notice that in EMO, in order to fine-tune this decoder, for each training sample, the multimodal modeling LLM, which is this part, is used to generate this n visual embeddings in an autoregressive manner to feed into this image encoder as a condition of image generation training. So in order to train this decoder, every time we need to run the LLM for once to do an inference to generate this n visual embeddings. So actually, EMO2 is targeted on optimize these 2 parts. So looking to the EMO2's objective and architecture, the architecture is still a unified autoregressive objective, which is predict the next multimodal element. Either can be a visual embedding or texture tokens. And we will explain this in our later slides. So we just first focus on the model architecture. So in EMO2, there is a simpler architecture, which only has a visual encoder, an autoregressive multimodaling, and a visual decoder. And in order to bridge between the encoder and the LLM, what they did is that they connect these 2 components by pulling each image into an 8x8 image patches, followed by a linear projection. And what's more is improved from EMO to EMO2 is this decoder. So this decoder in EMO2 is actually trained as a token nether, like here. So it can be trained off the shelf without the language model, and we will look into this in the later slides. So Let's first look at the training objective of EMO2. So recall the training objective is predict the next multimodal element, which means given an unlabeled web scale corpora, which is D, which consisting of interleaved multimodal sequence x equals x1 to xn, they will first convert all these continuous 2D signals into a 1D latent embedding sequence U equals U1 to UM, where UI can either be a discrete text token or a visual embedding. And the goal is to approximate the likelihood of web-scale corpora PX with PU using the familiar the log likelihood we're already familiar with. So UI is always conditioning on all those previous use with the parameter. And there's two types of losses being used. For the discrete text tokens, there will be a cross-entropy loss. And if this is a continuous visual embeddings, a L2 regression loss will be used. So looking to the pre-training stages of the EMO2, for training EMO2, first, it will pre-train on image text and video text pair data with only captioning loss on the text tokens. And then it will phrase the visual encoder and only optimize the linear projection layer and multimodal modeling with both the text classification loss and the image regression loss. And looking to the visual decoding part, the visual decoder is trained to directly decode visual embeddings generated by the visual encoder into image like here. So unlike EMO, where each optimization step of this visual decoder requires an autoregressive inference of the language model, EMO2 visual decoding is actually just can be considered as a detokenizer. So there is no more language model will be involved in the training of this decoder. So for EMO2, there's actually two variants with two different training objectives. First, there is the EMO chat, which can be efficiently aligned to follow specific task instruction by fine-tuning on a conversational data. So for this instruction following chat, the training objective is like here, and there will be two special tokens being introduced, which is user and assistant, to help organize the data type. So for user, the instruction is multimodal tokens, which is a prompt and image. And for the since after assistant token is the answer that's expected to be generated by the model, and it's actually supervised by a cross-entropy loss during training. And there's also one more system message that varies between two major task categories, either academic task-oriented or a multimodal chat. And the other variant of EMO is EMO-Jane, which is capable of accepting a mix of text, locations, and images as conditions and generate image that are grounded in a specified text or subject. So for this EMO2Jane, the training objective is still the unified generative pre-training objective, which is predict the next multimodal element. But there is something different for the input. So the coordinates of each object is represented in image form by drawing the bounding box at a specified location on a black image. So we can look at one example as here. So this is the prompt. This is the original image. What's more is fed into the model is those bounding box for each object, like the man, the horse, the mountain, and the water. All this is actually highlighted in this black image. So finally, let's look at some evaluation on EMO2. First, let's look at the performance of this pre-trained base model. And we can notice that EMO2 with only 37 billion parameters actually outperforms Flamingo 8 billion and the IDE FICS 8 billion under all field shot settings with a much smaller model scale. And also, we can look at this controllable visual generation examples, and we can say actually Emo 2 has a much way greater performance compared to all other models. So now we are going to move to the third model in this part, which is InternVL. So InternVL's inspection lines in evaluating the vision encoder to align with the parameter scale of LLM. So in InternVL, it first investigate the issues with existing vision large language models. So we can notice that for most of the vision language models we mentioned previously, to bridge the vision models with the large language model, there is always a lightweight glue layers used. And such an alignment actually have several limitations. The first, there's always a disparity in parameter scales. For example, large language models can be up to 1,000 billion parameters, whereas visual encoders is only around 1 billion. This may lead to the underuse of a large language model capacity. And there is inconsistency between representations, as vision models are usually trained on pure vision data. And this kind of representation is usually inconsistent with large language models. And since the glue layers are usually lightweight and randomly initialized, this can be an inefficient connection, and then it may not capture the rich cross-model interactions and dependencies. So, based on that observation, we can first look at a very popular and famous lightweight glue layer, which is Q-Former. And I think Q-Former is introduced or mentioned several times in previous lectures. And so Q-Former is just a lightweight querying transformer that is used to bridge the modality gap. The goal is that the queries can learn to extract vision representation that is mostly informative of the task. So the Q-Former functions as the information bottleneck that feeds the most useful information to the LLM while removing irrelevant visual information. And we can clearly see how Q-Former acts as a bridge between image encoder and the large language model. So the capability of Q-Former to extract information from image encodings generated by image encoder determines how many useful visual information can be fed into a LLM. So the author in InternVL argued that as the Q-Former is just too lightweight, it may not be able to capture all useful information and dependencies between image encodings and the text. So then the InternVL is proposed, and we can first look at the overall architecture of InternVL. So InternVL has two main components. The first is a large-scale vision encoder called InternVL with a size of 6 billion parameters. And this is actually implemented with a vanilla vision transformer. And there's also a large language middleware, which is initialized by QLlama with a size of 8 billion parameters, and it is developed based on the pre-trained multilingual llama, and there will be a newly added 69 learnable queries and cross-attention layers that are randomly initialized. So the advantage of such architecture is quite clear. First, this is a parameter balanced vision and language component, as both of the two major components are around 6 to 8 billion parameters, and the QLlama can transfer image tokens generated by InternVL 6B to the representation that is aligned with the LLMs by initializing with the pre-trained weights of multilingual llama. And SQLlama has 8 billion parameters, which is like 42 times larger than a Q-Former. Even with the frozen LLM decoder, InternVL can achieve a promising performance on multimodal dialogue tasks. So looking into the training strategies of InternVL. So besides of this balanced architecture, the author of InternVL also introduced a new training strategy to help with better alignment between the vision encoder language middleware and the LLM. So the first stage is a vision language contrastive training. It will adopt the Llama 7B to encode the text at STF and use InternVIT to extract the visual feature IF. And the goal is to minimize the symmetric cross-entropy loss and the similarity scores of the image text pairs in a batch. And this stage allows InternVL to excel on contrastive tasks like zero-shot image classification, zero-shot image text retrieval. In the second stage, it's a vision language generative training. QLlama inherits the weights of Llama 7B in the first stage, and both the InternVIT and QLlama are frozen. So in this stage, only the newly added learnable queries and the cross-attention layers are trained with this filtered high-quality data. So the loss has three key components, which is image text contrastive loss, ITC, image text matching loss, ITM, and image grounded text generation loss, ITG. And this enables the queries to extract powerful vision representations and further align the feature space with large language models. And the last stage is the supervised fine-tuning stage, where the InternVL and QLlama will connect with the off-the-shelf LM decoder and conduct the supervised fine-tuning. So the interesting part of InternVL is actually it can act as a Swiss Army knife model, which means it can flexibly combine the vision encoder and language middleware and support various vision language tasks. So for contrastive tasks, InternVL C and InternVL G can be used. They're using the vision encoder or in combination of InternVIT and QLlama to encode the vision features. And for generative tasks, QLlama inherently have promising image captioning ability, and the queries of QLlama reorganize the vision representation from InternVIT 6B and play as a prefix text for QLlama. And finally, there's the InternVL chat motion can be either used with or without the QLlama for multimodal dialogue. So looking into the experiments conducted in InternVL, we only show some part of the experiments, and I think one of the most important experiments being conducted by the author is to validate the visual perceptual capabilities of InternVIT 6 billion, and we can say it's actually InternVIT 6 billion outperform all the SOTA methods available and achieve a really promising results on all kinds of data set. And there are other evaluations, for example, the evaluation on InternVL chat, and we can see that the overall architecture with a 6 billion vision encoder, a QLlama as the middleware and the LM has the most promising and best result from all the other models like Lava, Flamingo, and Bleep, and Instruct Bleep, which I think we pretty discussed it in the previous lectures. Okay, so the last model I'm going to discuss is Gemini. And one thing I want to mention first is that Gemini is actually only has the technical report available online, so there's not much detail about the architecture or like training strategy used in Gemini available. So what we'll focus right now is more like its quality and some evaluations. So Gemini is a family of highly capable multimodals, and there are three models with different sizes that can be used in different scenarios in this family. And so the they have Gemini Ultra, which is usually used for highly complex tasks, and Gemini Pro that is used for enhanced performance and deployability at scale, and Nano, which is for on-device applications. And Gemini Ultra is a really strong model, which has noticeable performance on various benchmarks, and it actually achieved new state-of-art results in 30 out of 32 benchmarks, while 10 out of 12 is text reasoning benchmarks, and all other image understanding, video understanding, and speech recognition and translation benchmarks. And one thing to notice that Gemini Ultra is the first model to achieve a human expert performance on LMMLU. So LMMLU is a benchmark that actually covers 57 tasks, including elementary and mathematics, US history, computer science, law, and more. So this actually requires the model to possess extensive word knowledge and problem-solving ability. So one example is like this. The model is actually given a physical problem and it's a handwritten notes, and the model is asked to reason the question step by step to judge whether the students answer it correctly, and if the solution is wrong, point well is wrong and given the correct solution, and also it asks to use LaTeX for math and run off the final answer. So this is actually a really comprehensive problem that tasks all sorts of knowledge from the model. So looking into the architecture of Gemini, so there's not a lot of information available. So in this technical report, it only mentions that Gemini is built on top of transformer decoders that are enhanced with improvements in architecture and model optimization. And notice that it's trained to support 32K context length, and it's trained to accommodate textual input interleaved with a wide variety of audio and visual inputs. So the visual encoding of Gemini models is inspired by Flamingo, Coca, and Poly, with the important distinction that the models are multimodal from the beginning and can natively output images using discrete image tokens. And until now, notice that the standard approach to creating multimodal models usually involve training separate components for different modalities and then stitching them together to roughly mimic some of these functionalities. Whereas Gemini is actually native multimodal and pre-trained from the start on different modalities like showed here. So looking to some evaluation on Gemini, and one astonishing performance we can focus is here, like Gemini Ultra can reach 90.4 performance percent of accuracy on the MMLU dataset, and we already mentioned the MMLU is like a really comprehensive evaluation dataset, and the human expert performance is gauged at 89.8%. And in this report, the author mentions that in order to achieve such great performance, there's kind of a like prompting technique being used, which is chain of thought with uncertainty routing on MMLU, where the model is asked to produce k chain of thought samples, maybe like 16 or 32, and then it will select the majority vote if the model is confident about a threshold. Otherwise, it will just defer to the greedy sample choice. And we can see that a Gemini Ultra with chain of thought routing technique actually achieved its best performance. And there is also evaluation of the multimodal capabilities of Gemini models using a diverse set of tasks requiring a multilingual understanding, cross-lingual generalization, and generation of tasks in multiple language. And beyond the translation, Gemini is evaluated also on math and summarization benchmarks across all valuable languages. And also, we are going to show like the strong multimodal ability of Gemini. So looking to the example, we can see that for this one, it actually shows the multimodal reasoning capabilities to generate plot lib code for rearranging the subplots, which reveal several capabilities like recognition, inverse graphics, instruction following, and abstract reasoning. And just as Google mentioned in its blog, like Gemini can be your personal tutor, creating step-by-step instructions, sample quizzes, or back and forth discussion tailored to your learning style. So looking at some evaluation on zero-shot image understanding and few-shot video understanding, and we can see Gemini actually achieved SOTA performance on all these benchmarks available. And here's an example of video understand where it's giving a video and it asks what kind of technique is being used for the person in this video. So this is actually not only test the Gemini's ability to take video as input, also like reasoning in the video. And also to review the multimodal ability of Gemini, we can look at the image generation and audio understanding performance, and we can see that Gemini Pro models is actually significantly outperforms the USM and Whisper models across all ASR and ASC tasks, both for English and multilingual task sets. And finally, after discussing all these models, let's have an overall comparison of all 8 models we discussed today in this LMM module. So we discussed Flamingo, which is the first large multimodal, Lava, which is which highlight the visual instruction tuning, InstructPlay, which also highlight the power of visual instruct tuning, and InstructionWheel visual feature extraction, Poly, which focus on scaling up the vision multilingual, and Poly 3, which use a contrastive trained visual encoder to ensure the performance of smaller scale, large multimodal, and Emo2, which has a strong in-context learning ability by scaling up the model, InternVL, which bridge the gap between vision encoder and large language model using a language middleware, and Gemini, which is natively multimodal. So we can see in this table, it actually just displays some performance on each model in different data sets, and various kinds of data sets like VQA, V2, which is a visual question answering, NoCap, which focus on captioning, GQA focus on graphic QA, and text VQA is like a text visual QA. Finally, I want to discuss the limitations of current large multimodal, which is the hallucination effect. So we first look at what is a hallucination. So hallucination is that model can generate text that is factually incorrect or nonsensical to the provided source content. Look at these 2 examples. For example, it asks who was the first person to walk on the moon, and we can see this model is just give a totally incorrect answer. And for this one, the user is actually giving a context and let the model to summarize the following article, but the summarization has a totally wrong information that is inconsistent with the context is provided, like the year, and it's 2006 from the model output, whereas in the context is 2023. So there are many possible causes of the hallucination. We are going to discuss 3 of them, which is data training and the inference. So for data-related hallucination, misinformation inherited biases within data sources, which means that the model tends to capture spurious correlations, demonstrate difficulties in knowledge recalling. And in the training of LM, LMs, the inadequate unidirectional representation attention glitches in architecture design, and also in the alignment phase, capability misalignment and the belief misalignment can also lead to the hallucination issue. Finally, the decoding strategy can also influence the performance of LLMs. So overall reliance on nearby content and the softmax bottleneck can limit the model's ability to express like diverse output probabilities. And this inherent randomness of decoding strategies and imperfect decoding representation can also be a possible cause of this hallucination. So that's all about today's representation. We discussed 8 current really popular large multimodal and point out all of their great contributions and some limitations. And thanks for listening.